Hello ladies and gentlemen, welcome to my lecture series Modern Gravitational Theory. This is lecture 2, co- and contravariant coordinates. This is a very important concept. In other lectures or in many books you find a rather inadequate presentation of this theme. Here we will discuss this very detailed. Last time we made a transition from flat into a curved space, and here we get a problem now. In Cartesian coordinate systems there is only one possibility to define coordinates. That means we have a perpendicular projection onto the lines, onto the coordinate lines here. Here you get x1, x2, this is a rectangle. Okay. But if we consider now a skew coordinate system, like here in the diagram, we can make a projection orthogonal to the axis. That means we have a rectangle here. So we get here x1 and here the x2 coordinate. But we have also the possibility to make a parallel projection. This projection line is parallel to the x2 coordinate line, and so we get here x1 and here the x2 coordinate, and we see these coordinates and these coordinates are not the same, they are different. And now this is now very important. If we make this projection with the rectangle here to the axis, then we write the index as a lower index, the coordinates here, and we call them covariant coordinates, components. If we have this projection here parallel, then we write the indices as upper indices, and we call them contravariant components of a vector. Okay. So we can write a vector as a covariant and contravariant vector. Depends on the kind of projection. Now we can write for the absolute value of a vector x, this, and especially we have here now this expression. It's a scalar product of the co- and contravariant vector, and a square root of course, because we would get the square of the length. And here we use the so-called Einsteinian sum convention. That means we don't write a sigma for a sum, like here. We skip this sigma, and if we have such a term with the same index as an upper and as a lower index in one product, then we automatically have to sum over all the components. Okay, here we are in the two-dimensional space. That means we have only two addends, we have only two coordinates. Okay, and so in the four-dimensional space we would have for this a sum of four addends. And now attention please, if we have a covariant index in the denominator, then that counts as a contravariant index, and vice versa. So we can write for the gradient we had last time, we had this expression here, three addends, because it was a three-dimensional space, and we could write a sigma from 1 to 3 and sum over, or we don't write sigma and use the Einsteinian sum convention, because the first part, the first factor, is a contravariant vector and the second one is a covariant vector. So we have in one product a co- and contravariant index, and though we have automatically to make a sum then. Okay, we could exchange the two indices, that would be the same like this. Now we want to prove that expression 33 is correct, that the scalar product of the co- and contravariant vector is indeed the length, or the square of the length of a vector. So for this we put both co- and contravariant coordinates into one diagram here. Now we apply the Pythagorean theorem and consider the rectangle triangle here with x, the hypotenuse, then a, and here x1 covariant. Here we have a rectangle. Okay, so we can write x squared is equal to x1 squared, one leg, and the other leg a squared here. And we can write that for the other coordinate, x2 squared, x2 covariant squared, plus b squared. Yeah, that's also x squared, the hypotenuse. And now we can use another rectangle triangle here. This diagonal here is only the x2 coordinate, the contravariant x2 coordinate. And so we can write for the smaller rectangle triangle here, x2 contravariant squared, that's this, is equal a squared, one leg, and the square of the difference between x1 covariant and x1 contravariant. That is written here. Okay, in analogy we get for the other coordinate, for the other triangle here, the same. And then we apply the binomial theorem, and we get for the square of the square brackets here these three terms. The same in the second equation, 38, 39. And now we don't want to know a and b, so we substitute them by 37. That means a squared is x squared minus x1 squared, x1 covariant. So that's what we have set in here, and we do the same in the second equation. And now we see here is minus x1 squared, covariant squared, and plus x1 squared. So these two squares are cancelling, plus and minus the same. And we can cancel them in the other equation here. And so we have only this. Only 3 indents now in the two equations, 40 and 41. Then we add the two equations. So that means on the left hand side we have x1 contravariant squared plus x2 contravariant squared. On the other side here we have x squared, that means 2x squared, and and the other terms here together on the right hand side. Now we see x1 contravariant squared and x2 contravariant squared are on both sides, left and right, so we can cancel them out of the equation. Then we have in each term the factor 2, so we can divide by 2, and though the factor 2 is cancelled. And then we write the negative indents here, x1 contra and x1 covariant, and x2 co and x2 contravariant, to the other side with a plus. And so we have on one side x squared, and on the other side these two indents, and we see that is what we had said. X squared, the absolute value of a vector squared, is indeed the scalar product of the co- and contravariant vector. Here we have written the contravariant indices in parentheses to distinguish them from normal exponents. But we won't do that from now on, because it is normally clear whether it is an index or an exponent. Now we consider the general definition. Here we had diagrams in which the co- and contravariant basis vectors obviously point into the same direction. In general, this is not the case. We had done that to make it clear what's the difference graphically between co- and contravariant vectors or components, and now we will do that more general. We have, of course, again a two-dimensional Cartesian coordinate system, basis vectors Ex, Ey. It's an orthonormal basis. And then we consider a new, not orthonormal basis, E1, E2. If E1 and E2 is an orthonormal basis, then indeed the co- and contravariant basis vectors are the same. They are then identical. Okay. So if we have two basis vectors E1, E2, or general Ei and Ej here, so the scalar product has any value is unequal 0 if the indices are equal, and the scalar product vanishes if the indices are unequal. If we have a normalized basis, then the E vectors, of course, have the value, the absolute value 1, the length 1. If we have an orthonormal basis, then we can write for the scalar product of two basis vectors the delta Kronecker. And here, in this case, we get exactly 1 as in case if the two indices are equal, and again 0 if the indices are unequal. So for an arbitrary vector A with the orthonormal basis Ex, Ey, we can write this. If we make a scalar product of the vector A and the basis vector Ex, then that means we project the x component of A here, and so we have here the x component multiplied by the basis vector, and the same for the second coordinate. We first suppose that E1 and E2 is an orthogonal basis, but not a normalized one. In this case, we can normalize the basis vectors to get an orthonormal basis. So instead of 46 here, we write now this, because we have to divide twice by the absolute value of the basis vector. Okay, because we have twice the basis vector in the numerator, and so we have to divide twice then in the denominator. And so we can define here new basis vectors. That means this is E1 contravariant and this is E2 contravariant. So that shows the reciprocity between co- and contravariant basis vectors. Then we have the same shape like in 46, but here we have now the contravariant basis vectors in the equation here. Okay. And here in this case, when we have an orthonormal basis, then co- and contravariant basis vectors point into the same direction, but they have not the same length. They are reciprocal to each other. And we suppose then the most general case that a basis E1, E2 is neither orthogonal nor normalized. So that means we have to generalize here 49, we can say. And now, yeah, please attention. The co- and contravariant components, and so the basis vectors, are reciprocal to each other. So it is defined, this basis vector EI covariant multiplied by another contravariant basis vector is Kronecker delta. Though that means we get 1 if the indices are equal and 0 if the indices are unequal. And yeah, especially in our considered two-dimensional space, this means that the vector E1 contravariant is orthogonal to E2 covariant and vice versa. And this is another situation than in the previous cases. So, and now we consider an example with numbers and make a two-dimensional graphic to that. Yeah, we say we have E1 covariant basis vector with the coordinates 2 and 1. Then E2 has the values -1 and 0.5. And we have another vector with the components 4 and 4. So now, first we have to determine the contravariant basis vectors. To do this, yeah, we use the relation here, 52. We can write for the E1 contravariant basis vector the scalar product of E1 contravariant and E2 covariant is 0, must vanish. And here the scalar product with the contravariant first basis vector and the first covariant basis vector must be 1. Here we see directly the reciprocity. Yeah, we can write the same for E2 contravariant here. And then we get, if we calculate E1 contravariant now, we have the two unknown values alpha 1, alpha 2 here in the vector. And if we write down here this scalar product must be equal 1, then yeah, we set in 2, 1 and the parameters here. And for the second scalar product that vanishes, we get this. So that means we have a system of two equations with two unknown values, linear equations that are very easy to solve. So we would get here for E1 contravariant the values, the components 0.5 and 0.25. In analogy, we can calculate E2 contravariant. Okay, here we have written for the unknown values beta 1 and beta 2, and so we get here as a result the components minus 0.5 and 1. Okay, and now we can determine the components of the vector A by calculate the scalar products. Yeah, AI covariant is then of course the scalar product of A vector and EI basis vector. So the vectors are known, we have them written above. So we would get A1 is a covariant is 12, A2 covariant is -2. And for the contravariant coordinates we would get A1 is 3 and A2 is 2. And now we draw that in a diagram to see what happened here. So here we see this is E1 covariant basis vector, and here this E2 covariant basis vector. They are not orthogonal and they are not normalized. They have another length than 1. Then we have here E1 contravariant, and we see it is orthogonal to E2 covariant. And so E2 contravariant is orthogonal to E1 covariant. Okay? And so we have two different bases here. Okay? And now we can draw two parallelograms into the diagram. We have here the light green parallelogram. That is a parallelogram with the covariant basis vectors. Here. The red one is vector A. And the dark green parallelogram is set with the contravariant basis vectors. That means this one here. Okay, yeah, because the A2 covariant component of A was negative, -2. So yeah, we have here to draw the component into the opposite direction of this vector E2 covariant here. Okay. We summarize now. If we have an orthonormal basis, then co- and contravariant basis vectors and the components of a vector are identical. If we have only an orthogonal but not normalized basis, then co- and contravariant basis vectors point into the same direction but have different lengths. They are reciprocal to each other. And the coordinates of a vector are then different too. If we have a basis that is neither orthogonal nor normalized, then co- and contravariant basis vectors are orthogonal to each other. The vector E1 contravariant is orthogonal to the line of E2 covariant, and the co- and contravariant components of a vector are different. Many students have some problems with the concept of co- and contravariant coordinates, so we want to consider a three-dimensional example now. And first we start with an orthonormal basis. First we have Cartesian coordinate systems with the basis vectors Ex, Ey, Ez, and then we define another orthonormal basis, E1, E2, E3. Yeah, for E1 we have 0.8 and so on, 0.4 and so on, 0.2 and so on. The E2 vector is minus 0.3 and so on, 0.8 and so on, and minus 0.2 and so on. And E3 has got the values at minus 0.3 and so on, 0.1 and so on, and 0.9 and so on. And yeah, because it is an orthonormal basis, the following equation is valid. If we calculate a scalar product between two unity vectors here, two basis vectors, then the result is a Kronecker delta. That means the result is 1 if the indices are equal, and it's 0 if the indices are unequal. And of course the absolute value of a basis vector is 1 here. And yeah, we can show that with a diagram. Here we have the 3 or 6 basis vectors in a diagram, E1, E2, E3, co- and contravariant. Yeah, E1 co- and contravariant is the same. Yeah, that's an exercise for the students to show that here this is an orthonormal basis. And now we suppose that we have only an orthogonal but not normalized basis. So we multiply all the components by a factor 2, and so we get here other values in the coordinates of the basis vectors. Now if we calculate the scalar product of two basis vectors, then the result is not 1 but unequal 0 if the indices are equal, and it is 0 if the indices are unequal. And of course the absolute value is greater 0 but not 1. The scalar product of the co- and contravariant basis vector is of course the Kronecker delta. That means if the indices are equal we have exact 1, and if the indices are unequal, 0. Though here we see the reciprocity between co- and contravariant vectors, basis vectors. And this means if we had multiplied by 2 to get the covariant basis vectors, then we have to multiply by a factor a half to get the covariant basis vectors. So here we have the covariant basis vectors, and in this case the co- and contravariant basis vector point in the same direction but they have different lengths. We see that in this diagram. The longer arrows, the longer vectors here are the covariant basis vectors, and the shorter ones are the contravariant. But for example, E3 co and contravariant point into the same direction. Then we come to an arbitrary skew basis. That means the basis vectors E1, E2, E3 are neither orthogonal nor normalized. So we have again the definition: the product of the co- and contravariant basis vector must be the Kronecker delta. And now we consider the following vectors, the following bases. E1 is 1, minus 1, minus 0.5. E2 is minus 1, 2, minus 1. And E3 is minus 0.5, 1, and 2. And we consider an arbitrary vector with the coordinates 2, 2, and 2. Now we want to determine the contravariant basis vectors, and we do that in the same kind like we have done that in the two-dimensional case. We look at the scalar products. If we want to calculate the first contravariant basis vectors with the unknown components alpha 1, alpha 2, alpha 3, we can calculate the scalar product with other basis vectors, and the scalar product must be 0 if we multiply the E1 contravariant vector with the E2 covariant and E3 covariant basis vector, and we must get the result of 1 if we multiply E1 contravariant by E1 covariant. So we get 3 equations for 3 unknown values, the alpha values, and that's easy to solve. We get alpha 1 is 2, alpha 2 is 1, and alpha 3 is 0. In analogy, we can calculate the components of the other 2 contravariant basis vectors. So that means we get the following result: E2 contravariant has got the values, the components 0.6, 0.7, minus 0.2, and the third basis vector, contravariant basis vector, has got the components 0.8, 0.6, and 0.4. We consider this in a diagram. Here we are. The blue vectors are the covariant basis vectors, and the green ones are the contravariant basis vectors. The problem here is we have many vectors in a 3-dimensional space, and we must here make a projection into a 2-dimensional plane, and so that's a problem to get a nice picture of them. And we don't draw the parallelepipeds now into this diagram because it would be too confusing to have all the lines here. Now this is an exercise for students. Try to arrange a three-dimensional diagram or model or whatever to make that clear. Now the E1 contravariant basis vector is now orthogonal to the plane that is defined by the covariant basis vectors E2, E3. And of course the same is valid for the other basis vectors. For example, E2 contravariant is orthogonal to the plane that is defined by the E1 and E3 covariant basis vector. Now we finish lecture 2. In lecture 3 we will introduce the metric tensor. Thank you for watching. See you next time. Goodbye.